Today we are talking about volume, and we're going to be finding volume by using a technique called cross sections. When we were finding the area of a region, we were using a definite integral because our definite integral was just adding up lots of tiny rectangles, and the rectangles were very, very tiny. We had lots of them, and our width of our rectangles was getting smaller and smaller and smaller. Now we're going to use that idea to find a volume, which means our definite integral will be adding up volumes of various shapes as the width again, which is called something else in this situation, gets smaller and smaller and smaller. So the diagram below has a region. The region's kind of hard to see. This is our region right here. And it is in the XY axis, coordinate plane. And then a solid is formed by creating square prisms and adding them all up. And there's one square prism drawn in there. So let's just talk about how we would find the volume of a square prism. Well, volume of a prism is always the area of the base times the height. So we just have to figure out what is what in this picture. So if we want to use the cross section as a square, that tells me that the base is a square. Which in this case, if the square is the base of my prism right here, that means that the height of my prism in this case is actually going to be delta y. Which means now we're going to talk about finding the volume of this thing. So the volume is going to be the side squared would be the area of the base, because the base is a square and the area of a square is side squared times dy. Now for this particular function, the side right here is x. I know that's difficult to tell, but we're going away from the y-axis, and that is in the x direction. So for us, the volume would be x squared dy. But x is actually going to be a function of y, so my volume is going to be f of y, a function in terms of y that would be x times dy, and that's the volume of one single prism, which means now we need to talk about our definite integral. We don't need this right here. So the volume of the entire solid would be a definite integral, and again I want to add these up. My dy is in here, which means my bounds have to be y values. And in this case, I'm starting when y is 0 because I start right here at the point 0, 0, and I go all the way across to here where y is d. And then I would have the volume of my prism. So this would be the volume of this particular solid created by square cross sections. So now I'm going to go ahead and look at an applet. I've put the links on your paper so that you can go ahead and play with these later if you want to. I've already got mine pulled up. But if you want to copy and paste that into your web browser to take a look, I recommend it. So here is an example of a cross section. We are bounded by y equals x squared, so you can see the parabola-like shape in blue. Y equals 4, which is our upper bound. X equals -2, and x equals +2. We could have just said we were bounded by y equals 4 and y equals x squared. That would have bounded our region. But what we have is we have these squares sort of coming up from this region. And when we do, we're going to find the volume of that square prism, and we're going to add them all up. And again, the square could be anywhere that we draw in, but we're adding up all of these squares, adding up all of these squares, all of them, all of them, all of them, from x is -2 to x is +2. And I'm going to go ahead and generate what this solid would look like. And if we were to just take all of these square prisms and add them together, we would end up with this type of a shape. Now, we don't have to have a square cross section. by using this applet, we could change the shape we were using. So let's go ahead and let's look at semicircles. That's a good one. So here we have a semicircle, and again, we're going to be adding up all of these semicircles from start to finish, from -2 to +2. And if I were to generate this whole solid by putting those all in, I'm going to create a solid that looks like this. So each solid is going to be different. They're going to look different based on the cross section that is chosen. So let's look at maybe equilateral triangles. So again, here's an equilateral triangle. We're going to add up all of these equilateral triangles that are created here. Let's create the solid, and this solid looks like this. Now, that is a solid that's being created, and what we need to work on as well, how exactly do we deal with the volume of this? So I'm going back to the handout, and in our handout, I'm on the next page. So we're going to look at example 1. We have a solid with a base bounded by the circle x squared plus y squared equals 4. And we're going to find the volume of 4 solids, each with a different cross section. I think I changed my mind on that. I think I only did 2, so sorry about that. It's only 2 solids. And we're always perpendicular to the x-axis, I think, in this example. So let's look at our base. So the base is actually the circle. So let's go ahead and sketch that. This is a circle. We know that by looking at the equation. We should know that the center of the circle is at 0, 0, and we should know the radius of the circle is 2. So I know I'm going to have a circle centered at 0, 0. I'm going to go from -2 to +2 on both axes. So here's my base. So we are going to find the volume of a solid created by using cross sections that are squares. We're using squares again. I'm going to go ahead and draw in a rectangle, and again we are perpendicular to the x-axis. So I draw in my rectangle so that I'm perpendicular to the x-axis. Question is, how long is that rectangle? What's the height of that particular rectangle? I know the width. The width in this case is going to be dx. Go like that. That's actually going to be the thickness of my solid. But I need to figure out, well, how big is this thing? Well, this is a y value. Going from here to here is a y value. And I don't have y yet. So the first thing I need to do is solve for y. So I have y squared is equal to 4 minus x squared. And then that tells me that y is going to be the square root of 4 minus x squared. So that's what this is right here. Well, how many of those do I really have? In this case, I actually have another one down here. So I really have 2 of those. So there's 2 ways to think about this one. We have 2 times the square root of 4 minus x squared is the entire height of the red rectangle. Or we can look at it as subtraction. The top curve will be y is equal to the square root of 4 minus x squared, while my bottom curve will be the negative of that. The bottom curve is going to be y is equal to negative square root of 4 minus x squared. So you can look at it as subtraction, the top minus the bottom, the big one minus the little one. So top minus the bottom is another way to look at this particular problem. At which point, when I work that out, I have the square root of 4 minus x squared subtract the negative square root of 4 minus x squared. And of course, when I'm subtracting a negative, I'm adding. And in total, that gives me 2 square root of 4 minus x squared. So what I would really like to do now is look at my square. So I have a square, and I know how long each side of my square is, because this side of my square is that. And I know that is 2 square root of 4 minus x squared. So to find the area of the base, I know the area of a square, which is the shape of my base, is side squared. And in this case, that's going to be 2 square root of 4 minus x squared squared, which is 4 times 4 minus x squared. If you were to square that out, you don't necessarily have to, which means the volume of the prism is going to be the area of the base times the height. And in this case, the thickness of the rectangle is really the height. So my height is dx, and the area of the base I've already found is the area of the square. So that's going to be the volume of a single prism. So now what I need to do is I need to actually find the definite integral of this. So the volume is going to be the definite integral. And what will my bounds be? Well, my bounds are going to be x's because I have a dx. And it wouldn't have mattered in this case. We're always going from -2 to 2 because I have a circle. And then I'm taking the volume and then dx. So at this point, I would just go ahead and use my calculator and evaluate this definite integral. And we have 4 times 4 minus x squared. And our variable is x, and we're going from -2 to 2. And we get this. 42.666, repeating, which is 42 2/3, whichever way you want to leave that. So that is the volume of this particular solid. Moving on to example 2. We have the same region, except now we are using cross sections that are equilateral triangles. So we have the same concept here. We need to start with the area of our triangle. The side of the triangle is the same as the side is in the square. So that's 2 square root of 4 minus x squared. Now, the problem is to find the area of a triangle is 1/2 base times height. I'm partially happy with that because I know my base. My base is 2 times the square root of 4 minus x squared. However, I don't know my height, but I know my 30, 60, 90 rules. Do you? Yes, of course we know our 30, 60, 90 rules. And if this is an equilateral triangle, then each of these angles are 60. And when I draw in the altitude, the angle at the top is bisected, making that one 30. Now, in my 30, 60, 90 triangle, let me go ahead and erase that for just a moment. I know that the entire base is 2 square root of 4 minus x squared, but that should tell me how big this is right here. That should be half of that. So that's 4 minus x squared, the square root of that. Now for my 30, 60, 90 triangle, we should know our ratios, hopefully. And for our 30, 60, 90 triangle, let me draw that over here. We have 1 square root of 3, 2. Hopefully we remember that. Which means my height or my altitude is going to be this side times the square root of 3. So that means my height is going to be 2 square root, sorry, not 2, 4, the square root of 4 minus x squared times the square root of 3. That's going to be the height of this particular triangle. So let's go ahead and write down the area of my triangle. The area of the triangle is going to be 1/2 2 square root of 4 minus x squared times the square root of 3 times the square root of 4 minus x squared. So when I simplify that, I get the square root of 3 times 4 minus x squared, because the square root of 4 minus x squared times the square root of 4 minus x squared is just 4 minus x squared, which is much prettier. And now I need to find the volume of the prism, which is the area of the base times the height, which is the square root of 3 times 4 minus x squared. And again, my height is my width, and in this case it is a dx still, which means now I can find my definite integral. My bounds are still from -2 to 2. I still have the same region that I had. Square root of 3 times 4 minus x squared dx. And again, I can just go ahead and use my calculator to evaluate that definite integral. So we evaluate our integral. and get 18.4752. Now, example 2, we're going to a different region, and you no longer have a diagram for this one, but we're okay. We can still do this. So we have a region created, bounded by y equals x squared and y equals 9. So we're going to start with a parabola. So we have our parabola, and then we have y is equal to 9. And at this point, I know that this x value is 3, and I know that this x value is negative 3. Question is, what squared gives me 9, and that will be 3. So we're finding the volume of the solid created by using cross sections perpendicular to the x-axis. So I'm going to draw in my rectangle. So here's my rectangle, and this is actually going to be the base of a two-dimensional shape, and that shape is a semicircle. So this is actually going to be the diameter of my semicircle, because these semicircles are coming out of the screen towards us. So what I need to do is I need to figure out, well, how big is that diameter? And the diameter is the part inside the parabola. So the part that's inside the parabola is going to be the top, or the green, minus the bottom, or the blue. So if I took 9, which would be from the x-axis all the way up, that's 9, I would want to subtract out from the x-axis up to the blue curve. I would need to take that away to be left with the smaller red piece there. And this right here is y is equal to x squared. So that means that my diameter is going to be top, which is 9, minus the bottom, which was the y, which is x squared. So I now have my diameter, but of course I'm trying to find the area of a semicircle, so I need to start off by finding my radius. And my radius is going to be half of my diameter, so I just divide that by 2. And then I need the area of a semicircle, and the area of a semicircle is half the area of a circle. The area of a circle is pi r squared, and the 1/2 tells me I now have a semicircle. And so that's going to be 1/2 times pi times 9 minus x squared over 2 squared. That's still the area of the circle, the semicircle. So now we need to find the volume of the prism, which is just that times the width. And again, the width right here is dx. So it's going to be 1/2 pi times 9 minus x squared over 2 squared dx, which means I can now find my definite integral. So my bounds are the x's or are they y's? So I come on over and I look at my width, and my width is a dx, so I'm looking at x's, so I need those green, -3 to +3 of 1/2 pi times 9 minus x squared over 2 squared dx. And at this point, I can pick up my calculator. Again, do a definite integral. Watch your parentheses, I would watch in this, because we have quite a few things going on. We have a 1/2 pi, and then we have times this whole thing being squared. 9 minus x squared is on the top, so I need parentheses around that, divided by 2. Close that parenthesis so I can square it. And then my variable is x, and I am going from -3 to 3. And so my definite integral is 101.7876. Be sure and write down any questions that you have so that we can talk about them in class, and I hope you have a wonderful evening.